It's great to be here again at Universal Radio, and I want to say thank you to the radio operators out there, the ham radio operators, etc., that have given great support, good recommendations, references with regard, good reviews with regard to the COMPACTenna. One of the things that has been mentioned is that those that have seen the other video from last year on the physics of the COMPACTenna, that they would like to know a little bit more about that. So this is what I'd like to do, and here we go. The general concept of this magnetic field focus of the COMPACTenna applies to the models that you just heard about with regard to their technical specifications, the bands that they cover, that kind of thing. There are a few specifics which I'll allude to as well, referencing the one model and the other model. Again, we're talking about the ham radio COMPACTenna models 2M/220/440 and 28 to 450. Again, is in reiteration, the 2M/220/440 antenna, through diligent effort in science, technology, and fabrication, covers the entire 2-meter band, the entire 440 band, and indeed also the 220 non-harmonic band in a 7.5-inch antenna with quite high performance. The 28 to 450 model covers the 10-meter band. In addition, it covers the non-harmonic 6-meter band, which is wonderful, the entire 6-meter band, 50 to 54 megahertz, the 2-meter band, the 220 band, and the 440 band, all in a 24-inch high-performing antenna. On the other video, what I described was the concept, the proven concept now, after a couple of decades, of the ability to maintain a more consistent signal in the environment, the world we live in, which is an obstructed environment. Buildings, trees, valleys, hills, and in fact a dynamically obstructive environment with things moving, vehicles, people, doors, all these type of things. In that video, we talked about the polarization diversity in the electric field and the spatial diversity in the electric field. And in this way, maintaining the usable signal strength more consistently to reduce flutter, dropouts, in analog, even more so in digital, these type of things. Again, very briefly, we talked about the minimum signal necessary in order to have the communication. We talked about the average signal that one has in this obstructed environment as they're communicating. We talked about intermittent, significant dropouts in this signal, 20, 30, 40 dB, these kind of things. And we talked about the focus better than on increasing the gain a little bit of the antenna, but still having these significant dropouts, and therefore not much effectiveness in the obstructed environment in maintaining 95% reliability or whatnot. We talked instead, or in addition, we talked about that instead you would want to do something entirely different. You would want to focus on these minimal signals, bring them up simply above the minimum signal or signal-to-noise ratio necessary for the radio apparatus, so that we now had a signal that was more of this nature. That was the theory. We talked about the design of the antenna to do so. We talked about the science that goes on and that style thing. Briefly, we mentioned that in the obstructed environment, with all the reflections, refractions, scattering, and whatnot of the signal, that at times we have switching of the polarization from vertical to horizontal, and that this switching of the polarization was much of the reason for the significant dropout. We also talked about spatial diversity. We talked about you can be in one location and have the signal in a slightly variant location, in fact a fraction of a wavelength, a very poor signal. And we talked about the goal to, in addition to having polarization diversity in the electric field, having spatial diversity in the electric field, a three-dimensional antenna, such that if one part of the antenna is in a bad spot, the other part is in a good spot, and together, both of these things could bring this focus on the minimal signals and bring them above that signal necessary for maintaining connectivity. And that's essentially the roughly half-an-hour video condensed into a few minutes. At the end, I talked about what about when there is a need for an antenna that's extremely small. How are we going to achieve this kind of a thing when we don't have significant three-dimensional construct to the antenna, and therefore the spatial diversity in the electric field is not something we can focus on in terms of the technology? We can have some electric field polarization diversity, but what I said was that the key is in the magnetic field. It has to be. That's what we have left. And I talked about how antenna manufacturers and designers through the 100+ years have been essentially silent about the magnetic field properties of their antenna because it isn't substantially useful with those antenna designs. But that this antenna design focuses indeed on having substantial effectiveness in the magnetic field. How is that done with this now patented technology? That's what people wanted to hear about. My fellow hams, I have a great sense of accomplishment in doing all of this in a 7.5 inch and a 24-inch antenna. This is how he did it. When we look at the magnetic field, there are two things to look at. One is having a substantial magnetic field component to the technology, but the other is to shape it, if I can use that word, in such a way so that it is usable in this non-line of sight obstructed environment. Both of those things are really important. Let's first talk about the magnetic field itself. Going back about 200 years to Professor Ørsted in Denmark, who first described the magnetic field produced when an electric current is passed through a wire. From Professor Ørsted's observations was then derived the left-hand rule, as many of us know, describing the direction of the current, the line of force, and the magnetic field. And again, the magnetic field being perpendicular or orthogonal, rough perpendicular 90 degrees there, to the direction of the electric currents. The same thing goes in the RF electromagnetic environment. The magnetic field relative to an antenna, so we take a standard quarter wave ground plane antenna. We have the high voltage point here. We talk about the electric field. We have the higher current portion here, and we talk about the magnetic field. As the electric field fluctuates, such as AC, like AC current, alternating current, so does the direction of the spin of the magnetic field. Two standard wire antennas are essentially poorly functioning in the magnetic field. But as we talked about in the first video, radio frequency is electromagnetism. Half of the energy is in the electric field, half of the energy is in the magnetic field. So if we could do something to reasonably utilize that magnetic field, it should make a difference. And it does. As I described, one wire to one wire is rather ineffective in taking the magnetic field seen by the one, generated by the other, and inducing current within the wire. Now we know much better ways, of course. Transformers of a variety of nature. Tesla was phenomenal in this regard. Not directly communicating the contents of the now issued patent, we of course have to use some kind of a coiling, but not in the standard fashion. But by doing so in an unconventional way, we are actually able to generate a multitude of magnetic fields at high current portions within these antennas. And in fact, we're able to do that with very small magnetic field resonators. How small? Not shaping this coiling into a footprint that's a quarter wave or larger in its, in this case, vertical spans, but instead something that is not just being a wire, of course, but something that is on the order of only 10 to 25% of the quarter wavelength, or e.g. 0.0625 wavelengths. Again, we have a 7.5-inch antenna that covers not only 220 and 440, but 2 meter band as well, very effectively. There are added components in there to accentuate this magnetic field resonator. And of course, with the 24-inch antenna, we have a 10-meter antenna that's very, very small, yet very effective. There is some lateral expansion of this magnetic field resonator, just as one sees on transformers and whatnot. But then there is the second part, and this is very key, that we need to create a substantial magnetic field capturing and producing resonator, but we also need to shape it. What do I mean by that? Well, let's go back to this again. electric field in one polarization, magnetic field in the cross or orthogonal polarization. Let's go back to this. So, with regards to the shaping in the non-line of sight environment, we need to go back to visualizing what happens to the electromagnetic wave as it traverses the environment, bouncing, reflecting, refracting, diffracting, and whatnot. All right. So we talked about if you have an antenna on a tower that's vertically polarized, and you have a receiving antenna over here that's vertically polarized, and we have obstructions and whatnot in between. We talked about the flip-flop of the electric field polarization. So, in the earlier chapter of my designs, we talked about being able to grasp the signal in the vertical and the horizontal and the cross-horizontal polarizations. Well, here's something really interesting. Let us say, then, that you have a COMPACTenna which in the electric field is substantially vertically polarized. Again, there is some electric field polarization diversity, but substantially vertically polarized. And if we have a standard antenna that's electric field vertically polarized with a not very effective magnetic field coupling going on here, if we then flip the electric field polarization, what happens to the magnetic field of that electromagnetic wave? That's the question. Well, it also flips. So instead of being essentially horizontal, it now becomes vertical. So now, with the standard antenna, not only do we not have coupling in the electric field, 20-30 dB plus down, we have magnetic field coupling that's already very poor, and now it is perpendicular or orthogonal to this magnetic field polarization. That's a really bad thing. So, if indeed we have an antenna, the COMPACTenna, that has a substantial magnetic field component, what would we have to do to make it substantially usable in this obstructed environment where, with the vertical or the electric field polarization switched to horizontal and the magnetic field being vertical, well, we would need the magnetic field in this antenna to be vertically polarized. But wait a minute. If you have a substantially vertically polarized electric field antenna, how do you make the magnetic field, or at least a substantial portion of it, also vertically polarized? Textbook knowledge is whenever you have electric field in one polarization, the magnetic field is in the cross polarization. That's what it does. And that's how, in such a small antenna, in the obstructed world, it's able to take that signal. You're losing it now by, in this case, the electric field polarization switching, and you're capturing its substantial magnetic field in the polarization that that magnetic field has also switched to. So that's what it's all about. That's the key. Substantial magnetic field, but substantial magnetic field parallel to the electric field in an extremely small wideband multiband antenna. Again, I want to thank you for the support. I've seen references on eham.net and radioreference.com and in person, and I'm very pleased to present these two antenna models for my ham radio fellows out there, ladies and fellows.